So thank you so much, Francisco, for the introduction, and thanks to Ari and the whole CIPHER team for such a great conference. So I'm new to the social sciences, so being here and learning from the experts has been really a great learning experience. So I'm really happy to be here. So I am going to be taking a little bit of an interdisciplinary approach and presenting the American Life in Real Time, which is a study that I lead. I would like to thank my collaborators, my co-authors on this presentation, Marco Angrisani and Mick Cooper, as well as my partners on this work, which is the overall Understanding America study, as well as Evidation Health. And it's really through these collaborations that make this possible. So there we go. So what exactly is digital health? So digital health involves the use of digital technologies such as smartphones, wearables, Internet of Things to develop individualized interventions for health and well-being. Digital technologies are continuously monitoring our everyday experiences, producing large volumes of data called person-generated health data. Now, if you apply AI and ML algorithms, artificial intelligence and machine learning algorithms trained on these very large data sets from thousands of individuals, and then you can apply that algorithm to a specific person to make individual level predictions or interventions based on that specific person's baselines and characteristics. And these interventions are then pushed to users using the very same digital technologies that are used to produce the data, and the very same data that are used to produce the data are then used to iteratively refine the intervention and measure the effect of the intervention over time. And this has actually many benefits. So there are many benefits to this approach. So first of all, it's low cost, reducing access barriers to healthcare. It's in situ, offering continuous monitoring outside of intermittent clinical care. Okay. Yeah, in situ, offering continuous monitoring outside of clinical care. Okay, focus on lived experiences and real-time biobehavioral interventions and objective measures devoid of implicit or explicit biases. Now, you only need to read an article about ChatGPT to know that there are reasons to be skeptical about this last claim. So while this is the ideal for digital health, the reality looks a little different. And it turns out that field-wide methodological biases systematically underrepresent minoritized populations. And this is largely due to bring your own device designs that are standard practice in digital health research, which creates selection biases. And just how bad is this problem? So if you look at self-motivated device ownership in the UAS, which does not need any introduction at this point in the conference, self-motivated device ownership is about 22% in the UAS, which is in line with estimates suggested by Pew and others. And self-motivated wearable owners differ significantly from the general population. They tend to be more female, more white, and with greater education. And there's a linear relationship between income and wearable ownership, as you might expect. And consequently, wearable owners are very different from non-owners, with essentially almost all of these variables being significant. Now, selection biases can also differ based on the type of wearable. Here we have Fitbit owners versus Apple Watch owners, and we find that Apple Watch owners are even more likely to be younger, educated, working, and with higher incomes. And so the second problem is, so one is the selection biases. The second problem is that advanced analytical approaches like AI and machine learning often rely on the use of complete cases, where data with a lot of missingness are eliminated from the analyses. However, we know that these data are not missing at random, and that device use and competency is strongly associated with socioeconomic status. So this creates a 1-2 punch. You have a non-representative population that becomes even less representative during the analysis phase. So in other words, AI and ML approaches can in fact amplify initial selection biases. And Obermeyer was the first to demonstrate that biased algorithms can lead to patient harm. So what's the gap? The gap here is that we really need fair, representative, and high quality person-generated health data sets critical for AI and ML benchmarking. And what this means is essentially FAIR is an emerging standard in computer science, and it stands for findable, accessible, interoperable, and reusable. And since computer science really relies on as much data as possible, this standard really stresses the need to move away from traditional academic silos and make data freely available and usable. Now, benchmark data sets are used to establish performance criteria for software tools to afford more transparency in a field that inherently deals with algorithmic black boxes. And so applied to digital health, there are several benchmarking standards that can achieve sociodemographic representation, such as probability sampling and hardware provisioning. But there are also benchmarking standards for rigorously labeling data, which allows for machines to learn from patterns in the data that are associated with whatever label you might be interested in. So for example, what are the heart rate signals that associate with an experience of stress? Now, there are only a handful of studies that meet FAIR criteria, but they only fulfill the benchmarking criteria to various degrees, with NHANES being fulfilling the most criteria for achieving representation. However, NHANES uses a cross-sectional design, but also a short wearable measurement period, which is going to be an important point to remember later on in this talk. So this is where the Understanding America study, American Life in Real Time study comes in. So essentially, we were trying to meet all of these criteria in our design. So what does this mean? So we started with a probability sample of about 1,000 adults. These adults contribute to periodic surveys, both through their normal UAS protocol, but additional monthly surveys for health and well-being that we have specifically for the study. We also provide them with a Fitbit device as an incentive, whether or not they already had a device. And Fitbit devices measure certain biometrics on a continuous basis. We also match contextual data temporally and geospatially to the Fitbit timelines. The infrastructure, which was built by our partners at Evidation Health, is also flexible enough to accommodate future data streams as long as they contribute these data, as long as they come from an API. And we follow participants for as long as they're willing to contribute to the study. And what this does is produce this benchmark data set that can then be used for rigorous modeling and intervention development. So how this actually works is we invite participants to consent and enroll completely through remote processes. So starting with the UAS, we balance the population across intersections of biological sex, age, education, and race. We oversampled certain historically underserved populations, such as individuals who were non-white and without a bachelor's degree. Consent occurred through a survey. Those who said yes were asked for their addresses and mailed a Fitbit device, and then given instructions on how to download the study app. This custom study app was designed again in collaboration with our partners at Evidation Health, who are experts in digital health user experience design. So once the participant downloads the study app, the rest of the process becomes pretty easy. The app itself walks the participant through the remaining enrollment steps, including downloading and setting up and linking their Fitbit device, at which point we can actually verify their enrollment on our servers. And once enrolled, study activities occur through the app. Push notifications are used for reminders, and participants can track their study activity through earned points, which they can then exchange for monetary incentives. So the whole thing is designed to be pretty sticky to keep the user engaged over long periods of time. So this infrastructure was really created as a tool for the interdisciplinary study of digital health questions across the R&D pipeline. So everything from panel management, which is the most relevant to this audience here, to then development of sensors, testing, tool building, and digital biomarkers, integrating your engineers, your computer scientists, your epidemiologists, and clinicians. And then all the way to health services, integration, delivery, and public policy. But since we're at CIPHER, let's focus on the first one through a series of research questions. And the first one being, given that we have developed this design through these FAIR standards and benchmarking criteria, what are the remaining sociodemographic, personality, or health barriers to participation beyond convenience sampling and bring your own device designs? And so we found that of consent survey respondents, about 64% consented and 50% enrolled with very few demographic differences. So in doing our associations through random forests and logistic regression, we found that older age was the only sociodemographic or health factor across a set of about 80 variables that was consistently associated with non-consent. Now, beyond SES and health factors, the only other variable we found that was associated with participation was device ownership. And here you can see that self-motivated Fitbit owners were actually more likely to consent, suggesting that maybe device familiarity may be driving participation. Now, moving beyond consent to enrollment, conditional on consent, our biggest source of loss to follow-up was the two-step process between consent and address confirmation to mail devices, about 7% of consents. But again, through our logistic regression and random forest models, lower education was the only factor that was associated with this loss. Now, looking at wearable owners, here we actually don't see any difference in enrollment conditional on consent. Now, finally, looking at participation in the study itself through provision of Fitbit data, we were actually really surprised to find no sociodemographic or health differences associated with Fitbit wear time in the first 90 days. This was actually very surprising to us. So with about 53% of participants having 100% wear time and another 40% within the desired 60% threshold that we ask of them. So this likely speaks to the engagement experience and the app experience, but we're going to be exploring this more in the upcoming months. Now, again, looking at device ownership, we find that here, in fact, self-motivated Apple Watch and other device owners were more likely to have more days of Fitbit data. And again, this is surprising because this is the opposite of what we see at consent. So in other words, Fitbit users are more likely to consent, but other device users have better participation once enrolled. So now moving on to the second question. So given that we have very few sources of differential participation, can the use of probability sampling and device provisioning mitigate the current inequities in digital health research participation? And the short answer is yes. So we found that the unweighted allele sample is largely representative, and most of the oversampled groups remained overrepresented in the final sample. The only, and again, given the differential participation finding, the only groups that we sort of missed our target for was seniors and consequently retirees, but we're going to try to specifically recruit these groups in future recruitment efforts. Now, if you compare this again to self-motivated device owners in the UAS, you can see that we do significantly better in terms of representation. Now, surprisingly, because we balanced our invitation sample on socioeconomic factors, sex, race, age, and education, we were really happy to see that we also were able to recruit a fairly representative population based on SES. Based on health characteristics, looking at chronic condition prevalence and the number of chronic conditions as measured by the HRS questionnaire, but also through health behaviors, health utilization, and cognitive scores. And again, if you compare this to self-motivated device owners in the UAS, you can see that, self-motivated device owners are much more likely to be healthier than the general population and the allele sample. So the main takeaway from the allele recruitment is that probability sampling and wearable provisioning leads to very few sources of differential participation and broad representation in a digital health sample. So finally, we wanted to look at, does providing these Fitbits constitute an intervention and sort of hamper the observational nature of the UAS? And here we find the answer is yes, but really only for those who had never owned a device before. So here you can see that non-owners are much more likely to be active in the first few weeks after receiving their device. And the interesting thing here is that we don't actually see this trend in step counts, only in activity minutes, suggesting that people don't necessarily change the amount of activity they do, just the intensity of the regular activity in response to receiving a device. And this difference becomes non-significant starting in week 3. So now going back to the NHANES point with its 8-day measurement period, we can start to see why a short accelerometer measurement period might be inherently skewed, and that you might need at least 1 to 2 months of data to actually have valid results. Now, I have just a little bit of time left, so I would be remiss to not give you a little taste of what we can actually do with this data using COVID-19 as an example. So here we have Fitbit time series data normalized to the participant's self-reported infection date. And we can see, if we look at 60 days before and 60 days after this date, and we look at the change from individual specific baselines, looking at resting heart rate on the top left, activity on the bottom left, sleep duration on the top right, and sleep efficiency on the bottom right. And you can see that resting heart rate increases at the same time as activity decreases, sleep increases significantly, but at the same time, the efficiency or how well you sleep plummets during this time. And there's actually substantial heterogeneity in this signal across different SES factors. Now, this is definitely invaluable for disease characterization and heterogeneities and disease experience, but from a methodological perspective, if you look at, for example, the sample size, you see that the incidence of COVID positive is 20 times higher in our sample than published BYOD studies that use the same sort of time period. And then finally, if you apply an algorithm that is used to detect COVID signals that have been produced by other groups, and you use it on our data, we find that the COVID positive signal is detected within 3 days of the self-reported date in 80% of the cases, providing a really important validation of the self-reported data. And then finally, I'll leave you with the fact that we can use this to develop predictive algorithms that are based on just the passive data collection. And this can be triggers for just-in-time EMAs, they can be triggers for just-in-time biobehavioral interventions, and they can allow for population-based disease surveillance. So with that, I will thank my very, again, in the spirit of interdisciplinarity, my interdisciplinary team, and would like to give a shout out to Marco, my collaborator on this project, as well as Eva, who managed to send out 1,000 Fitbits during the pandemic in the course of about 6 months. So thank you.